Hey everybody, hope last lesson went okay. I made some adjustments to my setup. Hopefully it'll add some clarification for you. So we're going to start off today with a sample diploma questions. So which of the following diagrams best illustrates the magnetic field around a solenoid? And feel free to pause this so you can try it on your own, and then I will explain the answer. Okay. So, first thing we need to do is use our old friend Pitbull to tell us that current flows from negative to positive. Okay, so we're going to draw on the direction of the flow of electrons. So it flows this way, it flows underneath here, and then it'll be coming on top downwards like that. This one flows underneath, it'll go down there and then flow that way, and then this one will follow this path and be going upwards there. So that's the key to starting this off. So you can see that it's either up or down, depending on the picture. So A and C are down, and B and D are up. So I'm just going to switch to my camera here so you can give a visual of the hand, right? So use an object such as a pen to sort of represent the solenoid there. And you can see that, make sure you use your left hand. There we go. So it can be either going up and curling around, or it can be going, it's hard to do. I'm going to stand up here. Or it can either be going down and curling around like that. And you can, I'm just going to focus on the up one because it's a lot easier in the position that I'm in. So if my current, which is my fingers, is going up and curling around, my thumb points to this side, and then the other way will be opposite. So we're just going to label those north and south that way. So going up, my thumb is pointing, I have a little east here, it's pointing east. So let's open up that again. So going up, north is this way, north is this way, which means south is this way. South is this way, and it's going to be the opposite if the current is going down. So north is this way, north is this way, south is this way, and south is this way. Okay, so now we just have to make sure that our magnetic field is in the right direction. So magnetic fields run from north to south. This one runs from north to south, south to north, south to north, south to north, which makes B the correct answer. Okay, so hopefully that clarifies that. Hopefully you didn't have any problems with that hand rule. And now we are ready to move on to a new lesson and a new hand rule. So explain quantitatively the effect of an external magnetic field on a current carrying conductor. Predict using appropriate hand rules. Yeah, we're going to learn a new hand rule. The direction of the motion, force, and field in electromagnetic interactions. And that's it. So a current carrying conductor with a current put through it will create a magnetic field. There's a little alliteration, right? So if we run a current through this wire, there's going to be a magnetic field that circles around it. And if you put a current carrying conductor, CCC, in a permanent magnetic field, the magnetic field from the permanent magnet and the magnetic field from the current carrying conductor are going to interact. Okay, so you can see that our current is going into the page here, like that. So I'm going to draw that on. So I'm going to use my first left-hand rule. Let me switch to my camera. So the current is going that way. So with our first left-hand rule, if it's going that way, we can see that it circles around in a counterclockwise. Maybe it'd be easier if I drew it. So this is going into the page. This will be the page here. And my thumb needs to point going into the page, and you can see that my fingers are going circling around counterclockwise like that. Yeah, that's a little bit easier. So it's going to go around counterclockwise. So it's going to go around this way. And we have a north magnet and a south magnet. Magnetic fields always run from north to south. So the magnetic field from our permanent magnet is going to be going towards the south. So I'm going to draw that. This is just a different perspective, more of a 2D perspective. So this is a magnetic field from my magnet. And then my induced current, my magnetic field that's induced from my current will go around in a counterclockwise pattern like that. Okay, so what we want to focus on is I'm just going to draw a little arrow here because it's going to the right from the magnet. Arrow here to the right from the magnet. We want to focus on these guys, right? So you can see that one is going to the right and one is going to the left. So that means that those are opposite fields, and those opposite fields are going to attract. And in this diagram, the only thing that can move is my actual current carrying conductor, my wire. So it's going to draw it upwards. It's going to feel a force upwards because those are opposites. Okay. These are the same. So my wire is going to move to repel this magnetic field, which will also draw it upwards. So what's going to happen in this situation is my magnet is going to move upwards. Sorry, I said that wrong. My wire is going to move upwards. Okay, so the wire feels a force from both sides that's upwards, and that's the way that it's going to move. So here's just a little summary of what we just drew on. So above the conductor, two oppositely oriented fields, these are opposite oriented fields, will produce an attractive force, moving my wire up. Below the conductor, we have like fields that it's going to repel, so it's going to repel away from that field. And in both cases, the magnetic force Fm is upwards, so we'll draw the conductor upwards. So doing that every single time is a little bit annoying. You could do that, but what we're going to introduce is a third left-hand rule for situations where we have a current carrying conductor, a wire, and a magnetic field. So to find the direction a force will act on a current carrying conductor in a permanent magnetic field, your thumb is the direction of the current, your fingers are the direction of the permanent magnetic field, and then your open palm shows the direction of the magnetic force. Okay, so you can see in the picture here, thumb is the direction of the current, fingers are the direction of the magnetic field, and our palm sort of lifts it up here, and that's the direction of the force. So we're going to start off with an example. So determine the direction of the magnetic force on a straight current carrying conductor below by indicating on the diagram. Okay. So first thing we need to do is magnetic field runs from north to south. So my permanent magnetic field is that way. These are going to be my fingers, and my current is going into the page. So this will be my thumb. And I'm going to switch to my camera so we can see what happens. So just like in the diagram, my current is going this way. It's going this north section here. So my thumb is going to point that way. And then what I want to do is I want to make my fingers go in the direction of the magnetic field. Like that, so my thumb points that way, my fingers point that way, and you can see that my palm is then going to push it down, and that's what's going to happen. So this wire is going to experience a force downwards. That's going to be my force magnetic, and that's our third left-hand rule. Okay, so try it yourself with the screen. Put your thumb going into your screen, put your fingers going to the left of your screen, and you can see that your magnetic force is downwards. I know this is tough to do with like the camera perspective and all of that, but we're trying our best here. So let's do another example. And this one's with the northeast-southwest. So a conducting rod with the current going east is placed in a magnetic field. We can draw on a magnetic field that runs from north to south. Okay, so you can see it's going downwards, and our current is going east. So this must be going east. So I'm gonna draw this, or I'm gonna switch to the picture. And that's why I had the northeast southwest on there to help with this situation. Okay, so our current is going towards the east. So that's my thumb, and then my magnetic field was going downwards, which is into the page. And when I do that, you can see that, well, my thumb is pointed that way, my fingers are going into the page, that my hand is going to push towards the south. So my magnetic force is towards the south, like that works. Right. Another way that I can draw this on, if I switch back to my other view, is you can see that this is my magnetic field, like that. And if this is north, this is east, this is south, this is west. This is kind of like a three-dimensional. That's a really bad N, but that's my north right there. Let me fix that up. There we go. That's my northeast, southwest. So this sort of corresponds to the picture. So my current is going east. Right? So you can do this. So make your thumb go into the page, left hand, remember. Thumb goes into the page. If you're on a computer, this helps. Make your fingers go downwards to the bottom of the screen, and you can see that your palm pushes towards the south. So our magnetic force is going to be that way. And you can see that they're all 90 degrees. They're all perpendicular to each other. So yeah, let's do some more examples. Let's do some board questions. Obviously you don't have your boards, but I'll do this on here. So find the missing axis. So my magnetic force is up. My magnetic field, my magnetic force we don't know. My magnetic field is up, and my current direction is east. So feel free to pause the video and give it a go yourself and see if you can fill in that question mark. Okay, so I'm going to switch to my camera so we can try this. So FM, we don't know. Magnetic field is up, and current is east. Okay, so let's switch to the camera. Okay, so first thing I'm going to do is I'm going to make my current go to the east here. So I'm going to point my thumb east, and my magnetic field, which is my fingers, is up, like that. And you can see that if this is my current carrying conductor with my current going to the east, then I'm going to push my current carrying conductor to the north. So the answer is north. Okay, so let's try another one. So our next one is find the missing axis. So our magnetic force is down, our magnetic field is north, and we want to find our current direction. So let's try this. Okay. So we can't start with the current. I usually like to start with the current, but we can't because we don't know it in this one. So I'll start with my fingers, and I'll make the fingers on my left hand go north, right? And I want my, I already have it set up properly. I want my force to push it downwards. So downwards to me is into the whiteboard here. So my fingers point up. My hand is going downwards, and you can see that my thumb is pointed east. So this one is east. That's my answer. My current would be going to the east. Let's try one more. So this is another term that you'll see is into the page and out of the page. So my magnetic force is into the page, my magnetic field we don't know, and my current is going to the right. Okay, so let's try this one. So first thing I'm going to do, I like to set up my thumb. My thumb is my current, and then my magnetic force is going into the page. So I feel like these are all the same. So my palm is pushing downwards, this being my page here. So I'm going to go into the page. So my thumb is pointed right, my palm is going into the page, and you can see that my fingers are pointed upwards. Usually if we use into and right, my fingers going upwards, so my magnetic field is up. Right? So north or up, depending on what the question is asking. So I hope that helps. If you have any questions, feel free to email me or comment on this, and I'll try to clarify it. Do your best. Okay. So we're going to do another lesson that's very similar to this with the third left-hand rule tomorrow. So we'll get a little bit more practice with it tomorrow. So hopefully tomorrow's lesson helps as well. So all we've done is hand rules, which give us direction of a field and current and force. So we're going to add a formula onto it where Fm equals ILB. So Fm is our magnetic force, current is I in amps, and L is the length of the wire in that magnetic field. Okay, so that's what those guys equal. And B, of course, is our magnetic field. The unit is Teslas, and it has to be perpendicular to the magnetic field. And I'll talk about what that means in a sec. So we can find this on our data book. Let me just grab the data book out. So you can find it on your data book under electricity and magnetism, and Fm equals ILB is the second one from the bottom there. Okay, so let's do a question that we're finding both the direction and the magnitude. So calculate the magnitude and direction of a magnetic force on a conductor with 10 amps of current running south, placed in a perpendicular magnetic field of 10 Teslas, running up-down, and 2 bar magnets of length 10 centimeters as indicated in the diagram below. Okay, so let's try that out. So first, let's get our direction. So it says that the current is running south. That's going to be my thumb, and my thumb is running south. And we have a magnetic field that's going up and down. Well, so I'm going to switch back to the picture here to see if it's up or down. So our magnetic field runs from north to south. So you can see that my magnetic field is going down. So it's going to be downwards like that. Okay. So I want to point my thumb south, and I want to make my fingers go downwards. So you can see that my hand is pointed towards the west. My hand would push this pen towards the west. So my magnetic force is towards the west. I'll do another way of doing that is we have our B field is downwards, and it said that the current is running south. So if this is north, east, southwest, our current is running south. Right, and then do this to your computer screen. So point your thumb into the computer screen, point your fingers downwards, and you can see that your hand is going to push it to the west. So our magnetic field is to the west. So hopefully one of those ways works for you. So now we're ready for our calculation. So we're going to use our new formula. Fm equals ILB. And it says that our current is 10 amps. The length of wire is 10 centimeters. Make sure you're in meters. And then our current, or our magnetic field, is 10 Teslas. So I think this is going to be 10, but I'll double check it in my calculator here. So I go 10 times 0.1 times 10, and our answer is 10. So this is an answer for force, so it's 10 newtons, and we figured out that our direction is west. So that would be our answer. So again, if you have any questions about that, just comment or email me and I will help you out as best possible. So only the component of the current carrying conductor that's perpendicular, so 90 degrees to the magnetic field, will produce any force. Right, so if we have a wire, so our magnetic field runs from north to south, so it goes straight down like that. So we could put in our wire in a whole bunch of different positions, right? So if I put my wire like this, it's a nice straight wire, it will all be perpendicular, so that's perfect, and all our force will go into that. If I did it at an angle like that, well, only the component that's perpendicular, right? Only that x component of this will actually show up. And if I put my wire in like this, well, it's parallel, that wire is going to experience no force. So it has to be perpendicular. It doesn't really come up that much. This is not in curriculum, and this just shows that you do this in university, that the cos theta there means that only that perpendicular component. So yeah, there are some little sneaky questions that you can ask on that, but we want the wire to always be perpendicular to our magnetic field. Okay. Okay, so here's another type of example. A 30 centimeter long copper wire has a mass of 40 grams and is carrying a current of 5 amps out of the page at a right angle to a uniform magnetic field. So you can see the right angle shows us that it's perpendicular, which it will be almost all the time. So this apparatus is placed in a strong magnetic field and the wire is found to levitate. Calculate the magnetic field strength and draw a labeled diagram. Okay, so let's try this out. Let me get my camera out and we will do this. So I'm going to draw this is my wire, and my wire is like that because it's going into the page. My wire, if this was my pen, my wire would be like that, and I'll draw it going into the page. So into the page is an X, so that's my current, and it says that it's 40 grams and carrying a current of 5 amps. This apparatus is placed in a strong magnetic field and the wire is found to levitate. So levitate means that it's stationary. So if this is a wire like this, it's going to experience a force of gravity downwards. And if it's levitating, then there must be another force that's equal and in the opposite direction. So that's going to be our magnetic force. So it wants us to draw a labeled diagram of this. That's the second part of this question. So I'm going to put my thumb as my current carrying conductor into the page, and I want my force to be upwards, right? And when I do that, I see that my magnetic field has to be going to the east, to the right of the page there, like that. So this must mean that we have a north magnet here and a south magnet here. So that would be a labeled diagram for this. And now if we want to do a calculation, because they're equal, because it's levitating, we can say Fm is equal to Fg. We break this down into our new formula, Fm equals ILB. You'll notice I use a handwriting L just because it looks like a 1 if I don't, so I use a handwriting L and then Mg down here. So we're trying to find the magnetic field strength, which is B. So I move IL down below. And the mass of our wire is 40 grams, so 0.040 kilograms. We can assume this is on the surface of the Earth. Our current that they give us is 5 amps. And the length of our wire is 30 centimeters. So again, we have to be in meters like that. And if I type this all into my calculator, 0.04 times 9.81 divided by 5 times 0.3, I get 0. How many sig digs do we have? 2. So 0.26, and it's a field, so it's Teslas. So this is your homework for these lessons. So we have left-hand rule questions, magnetic field, magnitude calculation, so FM equals ILP, and then here's a graphing example here for the third left-hand rule stuff. So good luck, and if you have any questions, email me or comment, and I will help you out the best of my ability.